Hi guys, welcome to Gatematic. In the previous lecture we have covered all the previous year gate as well as ESC problem from three-phase inverter, that is 180-degree conduction mode as well as 120-degree conduction mode. Now in this lecture we are going to cover the last topic of power electronics, that is the current source inverter. So I divided the current source inverter in three parts. Part A contains only for resistive load. Part B contains only for capacitive load, that is the purely capacitive load, and part C will talk about the natural commutation or load commutation, means we will connect a resistive load and in parallel with resistive load we attach one capacitor to provide a natural commutation, or you can say the load commutation. So let us understand the current source inverter including resistive load, that is the part A. This is the circuit diagram of current source inverter. Here T1, T2, T3 and T4 are the four switches, that is the thyristor switch, and you can see that there are no any anti-parallel diode are connected. Why it is not connected, I will let you know. First tell me about what do you mean by current source. According to the definition of current source, an ideal current source is that kind of source in which current is constant and it is independent of voltage, that is known as current source. Now if you will go to market and if you will say to the shopkeeper that give me 10 ampere of current source or 5 ampere of current source, then they will not give you, because there is nothing like current source available in the market, right? So we make the current source in with the help of voltage source only. What is our requirement? Our requirement is to provide a constant current, right? So we can provide a constant current by connecting one voltage source in series with large inductance, and the property of inductance, we know that it won't allow sudden change in current. So if I will connect voltage source in series with large inductance, then definitely the current produced across it will be the constant, means the fluctuation, whatever the fluctuation will be, inductor will try to reduce that fluctuation and will make the source current, that is the constant. So there is nothing like current source available in the market. We make the current source by using the voltage source in series with inductor having very large value. Got it? So I am assuming that this is the input current, that is a source current, and it is constant, means it is not depending upon the load. The value of Is will remain as it is. Now let us understand, if I will connect the load, that is the resistive load, purely resistive load, then what is going to happen. So let us try to understand the switching configuration of this, from where to where T1 T2 is conducting and from where to where T3 T4 is conducting. Fine. Let us see from 0 to T by 2, if, or you can say in a degree axis from 0 to pi, or in time axis from 0 to T by 2. So from 0 to T by 2 I am triggering the thyristor T1 and T2. So if I will trigger the thyristor T1 and T2, means this T1 as well as this T2 will be sorted, means this source current will flow from T1 something like this, and it will go to load, then along T2, then along the negative point of this. So this is my input voltage V in, that is the input voltage, and we can replace this voltage source in series with current in series with inductor with one current source. Okay, this is my current source having value that is equal to Is. We can replace this. So you can easily understand, from 0 to T by 2, T1 T2 is triggered, and the moment when T1 T2 will be triggered, then I0 will be equal to C. The actual current direction Is are in the same direction of current I0 assumed. Okay, I0 I am assuming from A to B, and Is is also flowing from A to B only. So I0 will be Is equal to Is, and it is greater than 0. I can say that. So see, from 0 to T by 2, I0 waveform is equal to Is. Similarly, I can plot the V0. V0 is equal to I0 into R, and here resistive load is taken. So waveform of V0 and I0 will be similar, and it will look like this, whose peak value will be equal to I0 into R. Now see, from T by 2 to T, what is going to happen. From T by 2 to T, I am triggering the thyristor T3 and T4. So if I will trigger the thyristor T3 and T4, then definitely this will be sorted and this will be sorted, then in that case I am assuming that the moment when I am triggering this thyristor T3 and T4, then T1 and T2 is open circuited, means by using force commutation we can open this T1 and T2. So whole source current, this is my is will flow along this direction and it will flow along T3, then it will flow from B to A across the load. So definitely I naught will be equal to minus Is, because the direction of I naught I have assumed that is from A to B, but Is is flowing from B to A. So I naught will be equal to minus of Is, that is less than 0, and V naught I have assumed from plus to minus, and actual direction of current is flowing from B to A. That means it is also less than 0, that is equal to I naught into R, that is also less than 0. So from T by 2 to T you can see that I naught is equal to minus of Is. I have plotted in the first waveform whose peak value is minus of Is, and in the same way V naught will also follow the I naught waveform, because here resistive load is taken and we know resistive load does not change the waveform of I naught and V naught, means whatever the waveform of I naught you are getting, the waveform will be similar to V naught and vice versa. Fine. So this is my configuration. In this way we can see that at the output of the terminal we are getting the AC current. See, AC current means from 0 to T by 2 it is giving plus wave, and from T by 2 to T it is giving minus wave. And if I will draw the x-axis in terms of degree, then definitely this T by 2 will be equal to pi and this T is equal to 2 pi according to AC. Now tell me, for any value of time, are you getting the source current in reversed? No, you are not getting the reverse source current. That means the source current is not flowing like this. It will not be opposite, because we know current source is unidirectional. Therefore the direction of Is, that is the source current, will remain as it is no matter what the output voltage will be. Fine. So that is the reason here no anti-parallel diode is required. We in all the voltage source inverter we saw that here anti-parallel diode was there. Why? Because the source current in that case I was getting reversed, means source current may be positive and negative in VSI, but in CSI you can see that source current will be fixed and the direction is also fixed. That means no anti-parallel diode in the switch is required. So no feedback diode is required in current source inverter. Are you getting this? So this is the case possible in case of resistive load. Now understand what will be my input voltage. I already told you that this voltage source in series with a high amount of inductor can be replaced by one current source whose value is equal to Is. So we don't know the voltage drop across this current source, that is the input source. So let us take the input voltage drop across this input current source will be equal to V in. Okay, this is my input voltage. Now apply the KVL. See, from 0 to T by 2, T1, T2 is triggered. So the moment when T1, T2 is triggered means apply KVL in this loop. So if you will apply KVL in this loop, then it will be equal to minus V in plus V naught is equal to 0. So in this case V in is equal to V naught. Fine. Now see, from T by 2 to T, what is going to happen? So from T by 2 to T, T3 and T4 is triggered. So apply KVL in this loop. See, now the loop has changed. So if you apply KVL in this loop, then it will be equal to minus V in and minus V naught is equal to 0. So from here input voltage will be equal to minus V naught. So from 0 to T by 2 input voltage will be V naught, and from T by 2 to T input voltage will be minus V naught. So see, from 0 to T by 2 input voltage will be equal to V naught, that is represented like this. Input voltage will be equal to the V naught waveform, and now from T by 2 to T input voltage will be equal to minus of V naught, and here V naught is negative, so minus of minus V naught will be equal to plus V naught. So this is equal to plus V naught, whose peak value is V naught only, that is equal to I naught into R, or you can say Is into R, because here in this case the peak value of I naught is equal to Is. So in this way we have plotted the waveform of I naught, V naught and input voltage. Now Tell me what is the difference between voltage source inverter and current source inverter you are getting. In voltage source inverter, feedback diode is required, but in current source inverter, no feedback diode is required, because here source current is not getting reversed. Why? Because we are assuming that the input side, along the input side, it is current source, not the voltage source. And in current source, the direction of current will remain same, the value of current will remain same. Got it? Now the second difference is, in voltage source inverter, load voltage, that is constant. No matter whatever the load you will connect, the load voltage will remain as it is. But in current source inverter, the load current will remain as it is for any kind of load, whether it is R load, C load, RC load, any kind of load. If you will connect any kind of load, then the load current will remain as it is, it will not change. Okay, that is the second difference. So these all difference you need to know. I will let you know each and every difference later on. So based on what we have studied till now, let us try to find some parameter related to this current source inverter. I have considered the resistive load. So first find the output RMS current. So see, the waveform of output current is something like this. So RMS value of this current, I naught RMS, I can easily find that is equal to IS only, whose peak value is IS. So find the RMS value, it will be IS only. Square the waveform, take average, take under root, you will get IS only. And these all concept I have discussed in the single phase full bridge inverter also. So no need to discuss again. So I naught RMS will be equal to IS, V naught RMS is equal to I naught RMS into R. Here see, load voltage is depending upon the load current, but in case of VSI, load current was depending upon the load voltage. Are you getting this? Now see the second point, that is conduction angle of each switch. See, from 0 to T by 2, T1, T2 is conducting, and from T by 2 to T, T3, T4 is conducting. So conduction angle of each switch will be equal to pi only. This is my pi. Is this fine? So conduction angle of each switch will be equal to pi, and conduction time of each switch will be equal to T by 2. Now see the third point, that is the average thyristor current, or you can say average switch current and RMS value of switch current. So see here, each thyristor is conducting for pi duration only. T1, T2 is conducting for pi, and T3, T4 is also conducting for the remaining pi. So I can say that each thyristor is conducting for pi only, and whose peak value is equal to IS, that is the source current. So IT average will be equal to IS by 2, that is the peak value of current IS, into from where to where it is conducting, from 0 to pi. So pi upon 2 pi will give you IS upon 2, and IT RMS will be equal to IS upon root 2. How to find these all things I have already discussed from the starting to end, so no need to discuss again. Fourth point is really important. Let us try to understand, that is the input voltage is always positive. See here what I got. Input voltage I got, that is equal to always positive, means it will be positive for any value of time. So if input voltage is always positive, and we know IS is always constant, that is the source current is always constant. So what is the power? Supply power will be equal to input voltage multiplied by IS. It is also positive for any value of time. That means power is always delivered from source to load. Here it is not something like load is delivering power to source. It will be not the case in case of resistive load. So for any value of time, power will always delivered from source to load, not from load to source in case of resistive load. So this is important. Fifth point is also important, that is the force commutation is required. What do you mean by force commutation? Means we put an external circuit in order to turn off this thyristor, each thyristor. So see why force commutation is required, because for any value of time we are not reversing the polarity of voltage across any thyristor T1, T2, T3, T4. We are not doing like that. That is the reason here force commutation is required. While in case of capacitive load, I will teach you the capacitive load. By considering capacitive load, you will see that for some duration T1, T2 is getting reversed bias because of this output voltage. So I will let you know. In case of resistive load, here force commutation is required, because see here from 0 to T by 2, which one is conducting? T1, T2 is conducting, and after T by 2, T3, T4 is conducting. So the moment when T3, T4 starts conducting, then see here output voltage I am getting negative, so polarity of voltage will be something like this. And if polarity of voltage will be something like this, then this voltage will appear across this thyristor T1, something like this. and also this voltage will appear across this thyristor T2, something like this. So see, when T3 T4 is triggered, then at T1 T2 the polarity of voltage across it is something like from plus to minus, that is it is in forward conducting mode because I have triggered the thyristor prior to T by 2. So therefore it is really necessary to turn off this T1 and T2 before turning on T3 and T4. So for that we attach an external circuit, because here load is not trying to turn off this thyristor T1 and T2. So we have to attach an external circuit, that means force commutation is required. Got it? So in case of resistive load, force commutation is required, means we will attach an external commutation circuit in order to turn off the thyristor T1, T2, T3, T4. Got it? Sixth point is Fourier series. So we can write the Fourier series expression of this output current I naught. This is the square wave, and it is similar to the single phase full bridge inverter having peak value Is. So I can write the Fourier series expression, that is equal to summation of n is equal to 135 to infinite 4 Is upon n by sine n omega naught t, and V naught of t is nothing but I naught of t into R. So multiply this by R, you will get the V naught of t, something like this. Now see, the fundamental displacement factor, that is the cosine of angle between B01 of t and I01 of t. So there is no any phase difference I am getting here. So cos of 0 will give you fundamental displacement factor, that is equal to 1. I01 RMS I can easily find 2 root 2 upon pi into Is, means this is my I01 max. Okay, so if I will divide this by root 2, I will get the I01 RMS. Now I can easily find the distortion factor G, that is equal to I01 RMS upon I naught RMS, and here I naught RMS is equal to Ia, so G will come out to be 2 root 2 upon pi, and TSD, that is equal to 48.43%. So TSD I am getting, that is same as the single phase full bridge inverter. Now seventh point is IT01 average, means here I am talking about the fundamental component. So let me draw the fundamental component of load current as well as load voltage. So fundamental component I already explained you how to plot. It will be sine wave, something like this. From 0 to pi it will be positive, and from pi to 2 pi it will be negative, and this is my I01 max. And I explained you in the single phase full bridge inverter, that is I01 max will be greater than Is. So these all concept I have already discussed, so I am not repeating again. Once you plotted the waveform of load current, fundamental load current, then you can easily plot the waveform of fundamental thyristor current. So see here, from 0 to pi I am getting the current in T1 and T2, and it is equal to something like this. I am talking about the fundamental only, I am not talking about the total. And this is my I01 max, and from pi to 2 pi I am not getting the current in thyristor T1 and T2. So each thyristor is conducting for pi duration only. Therefore I can find the fundamental component of average thyristor current as well as RMS thyristor current. This is nothing but the output of half wave rectifier, that is equal to I01 max upon pi, that is the average value, and RMS value will be equal to I01 max by 2. So these all concept I have discussed previously when I taught you the single phase full bridge inverter. Fine. Eighth point is fundamental power across load. No need to explain it again. V01 RMS I01 RMS into cos phi 1, as cos phi 1 will be equal to 1, so it will be equal to V01 RMS into I01 RMS. Now I01 RMS I can easily find by using this equation, and V01 RMS I can easily find by using this equation. Fine. Ninth point is total power across load. This is nothing but total RMS component of current multiplied by R. Okay, so I naught RMS chi square into R, or you can write the V naught RMS chi square by R. So this much concept you need to understand in single phase current source inverter containing R load. So what is the key point that you need to keep in mind? The key point is, in case of R load, we don't have natural commutation or load commutation possible. Okay, here force commutation is required, means we have to attach an external commutation circuit to turn off this all thyristor. This is the important point. And the second important point is, input voltage I am getting always positive for any value of time, and source current is always positive and it is also constant. So overall I can say input power is always greater than 0, means in this case the power supplied by this current source is always positive. That means power is always delivered to the load. Okay, so reverse case is not possible in case of resistive load. Second point you have to keep in mind, rest all point are remain as it is. That the concept I have already discussed in single phase full bridge inverter. So that's all about this lecture. In the next lecture we will take the capacitive load and we will see the behavior of output voltage as well as the change in Fourier series expression, whether force commutation or load commutation is required or not. These all things we will see in the coming lecture by taking purely capacitive load. Fine. If you understood the concept, then please like this video, and if you are having any doubt, then you can ask in the comment below or join our Facebook group for doubt solving.